It can be tough sometimes to see the relevance of chemistry in the outside world, but electrochemistry is all around us in the world. As a matter of fact, electrochemistry is almost everywhere we look. Everything nowadays with a battery, from cell phones, watches, and even computers, can relate to electrochemistry. I'm James.
I'm Shelby.
I'm Corbin.
I'm Caitlin.
And this is Draw My Chem, Electrochemistry 101. But that doesn't really mean much unless you know all of those words. Electrons are negatively charged particles that carry electricity in solids. Ions are charged particles that can remain dissociated in solution. Some reactions happen naturally. We call these thermodynamically favorable or spontaneous reactions, but the true definition of a thermodynamically favorable reaction is that the reaction takes place without any outside input from the surroundings. Other reactions take outside force to occur, and these are not thermodynamically favorable reactions, or they are otherwise called non-spontaneous reactions. This section is tough to explain without a visual. But before we start, here's a joke for you. What are cations most afraid of? The answer is a dog ion. A great example of an item that has a lot of relevance to electrochemistry is a rechargeable battery. You can find these in laptops, phones, and all the way down to those little batteries in your remote that you can recharge. When the battery is supplying power to a device, it is acting as a galvanic cell, but when the battery is charging, it is acting as an electrolytic cell, but we will talk about that more later. First, we'll hear from Shelby on galvanic cells.
So, a galvanic cell generates electrical energy through its two parts, the anode and the cathode, and the electron flow between them. An anode is where oxidation takes place and is a negatively charged electrode in the cell. The anode, for example iron, loses electrons and they are transferred to the cathode through a wire. The charged electrode then becomes less negative. The cathode, an example is copper, is the taker of electrons and is where reduction occurs and the electrode becomes less positive. As the reaction progresses, the charges of the two electrons becomes closer to neutral. Once the charge becomes completely neutral in the electrodes, the battery dies just like a phone battery. To recap, reduction occurs in the cathode and oxidation occurs in the anode. Electrons no longer flow between the cell parts. Now, there's this thing called a salt bridge that sits in the solution of the anode and cathode. Salts are ionic compounds made up of oppositely charged ions. The purpose of the bridge is to balance the charge of the solutions completely. Here's an example. Sodium is a positive ion and flows into the negatively charged solution to keep the overall charge of the cell neutral. When the positively charged solution has more cations, then the chlorine molecule flows into the positive solution to keep the overall charge neutral. Remember, like charges repel each other, so the chlorine would not go into the negative solution because chlorine has a -1 charge. Why did the white bear dissolve in water? It was polar.
To make things even more confusing, an electrolytic cell is basically the opposite of a galvanic cell. An electrolytic cell is an electrochemical battery that uses electrical energy to create a non-thermodynamically favorable redox reaction. For the cell to be an electrolytic cell, an outside energy source must be applied. Since this outside energy is applied, the electrical current flows in the opposite direction, but is still going from anode to cathode. This is still true because the definition of an anode in an electrolytic cell is a positively charged electrode which the electrons leave, causing it to become more positive. The cathode is still taking electrons and becoming more negative. Reduction and oxidation still occur, but the reaction is not thermodynamically favorable because it doesn't occur on its own. Electrolytic cells, like galvanic cells, have a wire and a salt bridge. The only difference is that the wire is connected to an outer energy source, which drives the redox reaction in the opposite direction that it occurs in a galvanic cell. This is how electrolytic cells are rechargeable. The half reactions are both reversed, making the overall reaction not thermodynamically favorable. Like Shelby said, the salt bridge is there to balance the charge of all of the solutions completely. And this is still true for an electrolytic cell. How about another joke? Why did the chemist's pants keep falling down? He had no acetol.
No, God! No, God, please, no! 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 No!
Electrochemical reactions are made up of two half reactions. One reaction is oxidation and the other is reduction, as you have heard from Shelby and Corbin. These numbers are determined by assigning oxidation numbers to compounds and elements and finding the elements that increase and decrease in charge. Your chem teacher probably gave you a super long list of these things called standard reduction potentials. You'll need these for this problem. The reaction that decreases in charge, aka the reduction equation, should have electrons as reactants. Oxidation equations lose electrons, and electrons will appear as products. Here's an easy way to remember this. Leo the lion says grr. Anyways, E0 is measured in volts, and it tells you the total cell potential for reactions by finding E. The cell potential of the reduction half reaction should be somewhere on your list or given. The oxidation half reaction should be on the sheet in the reverse. Change the oxidation half reaction's standard reduction potential to a negative because you are reversing the reaction and the electrons are on the product side. Add the two standard reduction potentials together to find the E0 for the cell. It's a piece of cake. Here's an example. Here are two half reactions. Zinc 2 plus aqueous plus 2 electrons yields zinc solid, and the standard reduction potential is negative 0.76 volts. The other is Cu 2 plus aqueous plus 2 electrons yields Cu solid, and the E0 value is positive 0.34 volts. Zinc is being oxidized in this reaction, so you can change the equation to its reverse. Then I took the opposite of the E0 of the oxidation half reaction, which would be positive 0.76 volts, and added it to the standard reduction potential of the reduction half reaction, positive 0.34 volts. Then I have 1.10 volts as my total cell potential. You may have to multiply reactions in order to cancel electrons in other redox reactions, but do not multiply the E0 values by this number. Don't do it. E naught is a ratio, and you can't double or triple ratios. It's just like how you can't double or triple molarity. Did you hear that oxygen and magnesium got together last night? OMG.
Don't worry, we're almost done. When it comes to calculating delta G or Gibbs free energy, the formula delta G cell equals negative N times F times E naught cell is used. Delta G will be negative if the reaction is thermodynamically favorable and positive if the reaction is not thermodynamically favorable. The E naught value of the cell will have the opposite sign of the G value if the cell is galvanic. If the cell is electrolytic, then the E naught value will be negative and will have the same sign as the G value. N is the number of moles of electrons. F is the Faraday's constant, so that will always be 96,485 coulombs per mole of electrons. And E naught is the sum of the standard reduction potentials, like Caitlin explained earlier. So that's the gist of electrochemistry. Let's recap. So we basically taught you that electrons are negatively charged particles that flow and create electricity. In galvanic cells, electrons travel from anode to cathode and the reaction is thermodynamically favorable, and for electrolytic cells, electrons flow anode to cathode, but they are not thermodynamically favorable. To calculate the cell potential, you need to have an oxidation and a reduction half reaction and their standard reduction potentials. Change the sign of the oxidation half reaction and add the two E naught values together to get the total cell potential. Thanks for watching this episode of